Okay, hello everyone. I'm going to be talking to you about workforce management, which is a tool that Connex One are looking to implement into our platform. It does exactly what it says on the tin. It's a tool for to allow our customers to manage their workforce. It's going to be packed full of features, but I'm just going to be talking to you about the AI side of things. But before we get into that, I'm going to talk about myself. I'm Muzzy. I'm a data scientist at Connex One. I am also a technical lead in the forecasting department. I've got undergraduate degrees in law and physics. I've also got a master's in applied data science. After I completed that, I was very lucky to be offered a job by Dimitri. 2 years later, I'm still here. I still enjoy my job. I still enjoy coming into the office. And I still enjoy being part of the Connex One family. I might be biased, but I think it's a great place to work. But that's enough about that. So WFM, the AI side of things, research tells us, our customers are contact centers, and research tells us that one of the operational pain points for contact centers is scheduling. If you have a small number of employees and they're all homogeneous, then it's probably a very simple task. But once you start to increase the number of agents that you need to schedule, each of them have their own requirements, availability, skill sets, and they all pay different amounts, then the complexity of the problem just explodes. So what we want to do is try to alleviate that problem for our customers. But in order to answer the scheduling question, when should each agent work, first we need to be able to say how many agents do we need to meet the demand in any given period. But in order to answer that question, first of all, we need to say how much demand can we actually expect, which falls into the domain of forecasting, which is what I'm going to be talking to you about today. So as has already been mentioned, contact centers today offer not only telephone interactions, but also chat, email, SMS, and also a whole umbrella of social media interactions as well. The AI tool that we are going to create at Connex One will not only forecast voice, but forecast all of these different channels. So how do we do forecasting? Well, basically, all forecasting methods use historical data to predict future data. That's literally all it is. There's a whole edifice of complexity that sits on top of that, but once you strip that away, under the hood, that's all that's happening. Now, forecasting is a noble art. It stretches way back to time immemorial. The first recorded forecasters in history were the ancient Babylonians, who in 650 BC used cloud formations to predict short-term changes in the weather. Obviously, that's a long time before machine learning was ever a twinkle in the eye of some academics back in the 1960s. So I've listed some machine learning and non-machine learning methods over here, along with their advantages and disadvantages. Some of you are probably sat there thinking these machine learning methods are not machine learning methods, these are classical statistical models. Some of you are probably thinking that this distinction between ML and non-ML is quite simple, arbitrary, maybe, almost to the point of being misleading. To those people, I say this, I could not agree with you more. I think you're quite right. Not only that, I'm going to hopefully demonstrate that for you over the course of the next few slides as well. By first of all talking about some of the non-machine learning methods over on the left. So first of all, let's talk about the historical mean. This is probably the most simple forecasting method that you could possibly think of. I'm going to demonstrate it on the data that we have at the bottom. This is actual real data for incoming voice interactions. It probably spans a period of about 18 months. The data has been aggregated on a weekly basis. The data in orange is our what we imagine to be our past data. The data in green is the future data that we pretend that we don't know about yet. And so to create a forecast with the historical mean, we just take the average of all these values in orange and say that that's represented by the blue line over here. And we say that this is our forecast for all future values extending out to eternity. As a forecasting method, it's pretty rubbish, to be honest with you. So why am I telling you about it? Essentially, it's because I don't want you to focus on the technique itself, but there's a very important assumption that underlies this technique, which is that this assumes that all our historical data is useful and it's all equally useful. And that's the thing that I want you to kind of keep in your mind as we progress through the talk. In contrast, on the right-hand side over here, we've got our random walk model, sometimes referred to as a naive model. In this scenario, we're using exactly the same data. We're at the same point here, and we want to forecast into the future. What we do is we take our current value in the time series and say that this is our forecast for the next value. Then we move time forward by 1 unit, and then we say then we just keep repeating that process. So, for example, if we've received 100 calls this week, we say that our forecast for next week is also 100 calls. And then next week, if we actually receive 90 calls, then that becomes our forecast for the next week. So with this technique, we can only forecast one step ahead. Again, it's probably not. You can see the results in blue again. It seems to follow the actual data quite well, but it's got the limitation that we can only forecast one step ahead. Again, there's the technique itself is probably not important, but there's a very important assumption that underlies this as well, which is that we're assuming that none of our historical data is important, only our current data or our current value is important for future forecasts. So as I said, both of these forecasting methods are pretty rubbish, to be honest with you. And what we probably want to do is combine the assumptions that underlie them rather than the actual techniques themselves. And most forecasting methods I can think of do, in fact, combine these two assumptions in some intelligent way. The best example I can think of are exponential smoothing models. These assume that all historical data is useful. So along the x-axis here, we've got time, and this also represents our data because we're talking about time series. The exponential smoothing models assume that all of this data is useful and we're going to use all of it. However, we're going to place more importance on the more recent data by giving that data a greater weight. So you can see, hopefully you can see here, these are our most recent past observations. These are the highest weights, and these decay as we progress backwards in time. And the decay is exponential, which is why we call this an exponential smoothing model. So I hope you can see how here, this is what I call a machine learning model. We've combined the assumptions from our very naive, simple forecasting techniques from the previous slide to create something that's more interesting, more flexible. And what we do is we don't want to sit down and handcraft all of these different weights manually. We want our machine to learn these, to infer these from the data. There is a parameter in most machine learning, in exponential smoothing models, which controls how fast the weights decay. And this parameter is inferred from the data. So while some people might call exponential smoothing models classical statistical models, I refer to them as machine learning models. And we can agree to disagree on that if... So I'm going to show you an example of a forecast created using Orbit, which is a package developed by the lovely folk over at Uber. They use it internally to do to forecast all sorts of wonderful things. They've open sourced it so people like me can be nosy and poke around in there. Orbit is not really a model in itself. It's a framework for inference. Currently, they have 4 models which sit on top of that framework. All of them are exponential smoothing models, just like we've been talking about in the previous slide. The one I'm going to show you an example of today is called the damped local trend. It is a additive model, which basically means that we have our structural equations on the right here. Y is our target variable. It's our time series that we're trying to forecast. And in order to generate that forecast, all we're doing is adding a bunch of components together. I've listed some of these components on the right-hand side over here, including trend, seasonality, regresses, error, level, and so on and so forth. It would be remiss of me not to mention that Orbit is actually a acronym. I'm not sure what the other stuff stands for, but the B definitely stands for Bayesian. So this is a Bayesian time series forecasting model. I thought it was important to point this out because most of the models, whether time series or non-time series, you see out there in the wild are frequentist models, whereas this is Bayesian. Now, the difference between Bayesian and frequentist statistics could make up an entire semester of an undergraduate statistics degree. I can't say statistics for some reason. It's probably, I'm probably going to skip over the finer points and just give you a high-level overview. In the frequentist world, we try to infer, estimate model parameters, but for frequentists, those parameters are fixed numbers. In the Bayesian world, model parameters are not fixed. They are distributions, like we can see over here. The advantage of that approach is that uncertainty is built directly into the model by design. Frequentists will try to estimate model parameters by looking at the data. So do Bayesians as well. But before Bayesians ever see any data, we can also incorporate prior information. So what do I mean by prior information? Well, that could be human intuition. It could be the forecaster's domain knowledge. And I think that's a really important point, because in this world of ChatGPT, where we've got headlines of AI taking over the world, this is a way of keeping humans in the loop. So I think that's very important. So how do we incorporate that prior information that we have into our forecast? Well, we make an initial guess about the distribution of our data and the parameters. So for example, we talked about the smoothing parameter in our exponential smoothing model that controls the decay of the weights. If you as a forecaster have expert knowledge or domain knowledge or some kind of intuition about how that should be, we can specify a distribution, and then that's before we ever see any data whatsoever. So that's the other big advantage of Bayesian forecasting, which is that you don't need a lot of data to be able to produce a good forecast, because you can incorporate that prior information. So essentially what happens is probably this slide is quite confusing, so I'm going to give you a real-life example. For example, when I wake up in the morning, typically what I do is I look at my phone and see what is the percentage chance of it raining today. So my phone might tell me it's a 50% chance of rain. So that's my initial belief about whether it's going to rain today. Then what I typically do is I open the curtains, and that gives me new data. If it's cloudy, then if it's overcast, then I can say my new belief about whether it's going to rain today is probably 60%, whereas if the sky is clear, then I'm probably thinking, well, it's probably 40%. So essentially, it's the initial belief is updated by new data, and that gives me an updated belief. So in technical terms, the prior distribution plus the new data gives you the posterior distribution. So that's what's happening under the hood. So enough theory. Let's move on to some actual data. This is again contact center data, incoming voice interactions. We can see the daily profile of calls. We've got a full week's worth of data in the middle over here, and then a full month's worth of data on on the right. So we're going to be use this data and the orbit forecasting model to forecast into the future. Before we do that, we're going to do some pre-processing. We're going to resample our data into hourly bins. We use a sliding window approach for backtesting, so this is slightly different from what data scientists normally do, which is cross-fold validation. We can't do that. We can't do cross-fold validation on time series because the order of the data matters. Once you change the order, if you shuffle the data, then you lose the time series. So essentially, what we do is we've got all our data across the bottom here. We've got each window is comprised of our training set in the light-colored bars, and our test set is the purple squares at the end. For each split, we do training and test, and then we move the window forward and we slide it across our data. So that why do we do that? Well, it's good practice because it mimics what would probably happen in production, and it's probably the best way to identify how accurate our model is likely to be once we productionize it. So here's an example of a forecast that's been created using Orbit with the data that we've seen over the past couple of slides. The data that is the solid line is our actual data, and then the dashed line is our forecast. How do you think we've done? Well, I mean, looking at the forecast, I think we've got a good agreement between actual and forecast data in the first week. We've probably got on Thursday, the second week, we've over forecast, and then we've under forecast on the Friday. Of course, we're data scientists, so we want to quantify that. We've got our error metric here, which is our mean absolute percentage error, which is basically by what percent our forecast is inaccurate by. So here you can see that we've got a percentage error of about 25.7%. Is that good? Is that bad? A lot?
Seems like a lot.
Yeah. Well, I mean, it depends on your data. So sometimes you get really good data and you get higher accuracy. With this particular data set, we were able to get 25.7%. Typically, what you do is compare that to a baseline. In this case, we could compare it to the historical mean that we were talking about earlier. You can imagine that if we were to create a historical mean forecast for this data, it'd probably be a straight line going across the middle. The accuracy would probably be about 50%. So we've at least beat the historical mean anyway. So that's a win in my book. So because, as I mentioned earlier, the forecasting, the Orbit is an additive model. So you can, once you've created the forecast, you can go back and have a look at the analyze, maybe work out why it's accurate or why it's inaccurate. Some of the components I mentioned earlier, you can see here, the trend, our seasonality, our regresses. You can see for the trend, Orbit clearly thinks this is for a week's worth of forecasting. It clearly thinks that there's the trend is 0 for this week, but the shaded interval here is actually not the confidence interval. Confidence intervals is terminology from the frequentist world. What that really should say is our credible interval, which is what we use in Bayesian speak. But essentially, you can see it's quite certain that the trend is 0 at the beginning, but as you progress through the week, the shaded band gets wider. So it becomes less and less confident about what the trend is. In terms of the seasonality, the band is so narrow that you can barely see it. So it's quite confident that this is the seasonal pattern observed in the data. I've not really talked about what regressors we've used. It's really outside probably the scope of this talk, but essentially it's time of day, week, month info data that's been derived from the time series itself. And that essentially concludes my talk. So thank you very much, everyone.